This is the story of a measurement that should not have been possible with the equipment available in 1919. Two British teams sailed to opposite sides of the Atlantic to photograph a total solar eclipse, and what they were trying to detect was an angle roughly 1/2000th of a degree. A shift so small that if you stood in London and looked at a coin lying on a table in Oxford, the width of that coin is about what they were hunting for. They were looking for it on glass photographic plates, in tropical heat, using borrowed telescopes, with about 6 minutes to get it. Almost everything you've heard about what happened next is a slightly cleaned-up version of the truth. The famous version says the eclipse proved Einstein right. The more interesting version is that it didn't prove anything. It placed a very rough first bound on a number, and the actual proof took another 80 years and a spacecraft on its way to Saturn. Let's start with what they were trying to measure, and why it was so hard. In November of 1915, Albert Einstein finished the general theory of relativity and presented it to the Prussian Academy of Sciences. The central idea was that gravity is not a force pulling objects across space. Gravity is what happens when mass bends space and time themselves, and objects, including light, simply travel the straightest available path through geometry that is no longer flat. That last part is the testable bit. If space is curved near a massive object, then a beam of light passing close to that object doesn't travel in a straight line as seen from far away. It bends. Einstein calculated how much. For starlight grazing the very edge of the sun, the limb, general relativity predicted a deflection of 1.75 arcseconds. An arcsecond is 1/3600th of a degree. The full moon in the sky is about 1800 arcseconds across. So Einstein was predicting that a star's apparent position would shift by less than 1/1000th of the width of the moon. But here's what made it a genuine experiment rather than just a hard measurement. There were 3 competing answers on the table, and they were far enough apart to tell apart. The first possibility was 0. Light might not respond to gravity at all. If light has no mass, and gravity acts on mass, then perhaps starlight sails past the sun completely undisturbed. The second possibility came from treating light as a stream of particles with some effective mass, falling through Newton's gravity like everything else. That calculation gives 0.875 arcseconds, half of Einstein's number. It has a long history, and in 1919 the British astronomers presenting the results assigned it to Newton, on the reasoning that it's what you get from Newtonian gravity acting on light as particles. And the third possibility was Einstein's 1.75. So the experiment wasn't really, is Einstein right? The experiment was 0, half, or full. 3 outcomes, and if you could measure the deflection to better than about 50% accuracy, you could eliminate 2 of them. 50% accuracy, on an angle of under 2 arcseconds. In 1919, on glass. That's the problem. Now let's look at why it was almost unsolvable. To measure a star shifting position, you need to know where the star was before it shifted. That sounds obvious. It's also the entire difficulty. The stars you need are the ones whose light passes closest to the sun, the ones near the limb, where the deflection is largest. Which means that on any ordinary day, those stars are directly behind the sun and completely invisible, drowned in a sky a million times brighter than they are. This is why the eclipse matters. For a few minutes, the moon covers the solar disk, the sky goes dark enough for stars to appear, and for the only time in the year you can photograph stars sitting right next to the sun. But that gives you only half the measurement. You photograph the star field during the eclipse. Then you need a second photograph of exactly the same star field with the sun somewhere else entirely, so you have an undeflected baseline to compare against. And the sun moves out of the way on the sun's schedule, not yours. Which means the comparison plates get taken months apart. Different season, different time of night, different temperature, different air. Often, a different continent. You are comparing 2 photographs taken half a year apart and asking whether some dots on one are 1/1000th of a millimeter out of place relative to the other. Now stack the practical problems on top. The photographic plates are glass. Glass expands when it gets warm. The eclipse plates were exposed in the tropics, Some of the comparison work happened elsewhere, in different conditions. A temperature difference of a few degrees changes the scale of the whole image, and a scale change looks exactly like a radial displacement of stars away from the center, which is precisely the signal you're looking for. The thing that fakes your result is also the thing you cannot avoid. The telescopes themselves were a compromise. Rather than pointing a large telescope at the sky and tracking it, both teams used a coelostat, a driven flat mirror that catches the light and feeds it into a telescope lying horizontally on the ground. It's the practical solution for fieldwork because you can't ship a mounted observatory telescope to a jungle. But it puts a large flat mirror in the optical path, and mirrors held in the sun distort as they heat. A mirror that flexes by a fraction of a wavelength during totality will smear every star image on your plate. Then there's the sky. You need clear weather during a window of a few minutes on one specific day, in a location determined entirely by celestial mechanics, reached by ship, months in advance, with no possibility of rescheduling. There is no second attempt. If a cloud crosses the sun at the wrong moment, the expedition returns with nothing, and the next comparable opportunity is years away. And finally, after you have your plates, you measure them by hand. A micrometer, an operator, a magnified image, star by star, coordinate by coordinate, thousands of readings, each one a human judgment about the center of a slightly fuzzy dot, then weeks of arithmetic, with logarithm tables, to turn those readings into an angle. Every single stage of this is a place where a systematic error of the same size as your signal can enter. Which brings up the obvious question: why did anyone think it was worth trying? Because they'd already tried. Twice. And both attempts should terrify anyone who believes science moves in a clean line. In 1911, 4 years before he finished general relativity, Einstein published a calculation of light bending near the sun. He was working with an incomplete version of the theory. He had the equivalence principle, but had not yet worked out the curvature of space itself. That early calculation gave a deflection of about 0.87 arcseconds. The half value, the Newtonian value, the wrong answer. And Einstein actively encouraged astronomers to go and test it. An expedition set out for Brazil in 1912 to observe an eclipse and check the number. It rained. They got nothing. In 1914, a German team, led by Erwin Finlay Freundlich, traveled to the Crimea for another eclipse. They arrived, set up, and the First World War broke out while they were on Russian soil. German nationals, with optical equipment, in a war zone. They were detained, their instruments seized, and no observation was made. Sit with that for a moment. If either of those expeditions had enjoyed clear skies and a peaceful summer, they would have measured a deflection and compared it to Einstein's published prediction of 0.87 arcseconds. Had they measured accurately, they'd have found something close to 1.75, roughly double what the theory in front of them predicted. And the headline would have been that Einstein's light-bending prediction had failed the test. The theory that got confirmed in 1919 was saved, in part, by clouds over Brazil and a war in Europe. Einstein himself later acknowledged how narrowly he'd escaped. By 1915, with the full field equations finished, the number doubled. And this is one of the genuinely important things about the 1919 story that rarely gets told. The reason the factor of 2 matters isn't bookkeeping. The extra 0.875 arcseconds comes specifically from the curvature of space. The first half is what you get from time running differently in a gravitational field, the part shared with the older, simpler picture. The second half is space itself being bent. So the measurement wasn't, does gravity affect light? It was, is space curved, or isn't it? That's why the factor of 2 was worth crossing an ocean for. The 29th of May 1919 was, from an observational standpoint, an extraordinarily lucky date. The eclipse track ran across northern Brazil, over the Atlantic, across the island of Príncipe off West Africa, and onward across the African continent. Totality was long, several minutes, far more generous than the 90 seconds or so many eclipses offer. But the real luck was where the sun happened to be sitting. On that date, the sun was positioned in front of the Hyades, a bright, dense, open star cluster in Taurus. That meant an unusually rich field of measurable stars close to the solar limb, exactly what the experiment needed, and something you cannot arrange. Most eclipses put the sun against a sparse patch of sky, where you might get a handful of faint stars at awkward distances. This one handed the astronomers a crowded field. The report that came out of the expeditions noted plainly that these unusually favorable conditions would not recur, and that future attempts would have to work with fainter stars further from the sun. Britain's Joint Permanent Eclipse Committee had made the decision to send 2 expeditions back in November of 1917, while the war was still on. The Astronomer Royal, Frank Watson Dyson, drove the planning. 2 sites, because one site is one roll of the dice with the weather. The teams left Liverpool by ship in March 1919. To Sobral, in the dry interior of northeastern Brazil, went Andrew Crommelin and Charles Davidson of the Royal Greenwich Observatory. They carried 2 instruments, an astrographic telescope with a 16-inch coelostat mirror and a smaller 4-inch lens brought along essentially as a backup. To Príncipe went Arthur Stanley Eddington of Cambridge with his assistant Edwin Cottingham. Príncipe is a small volcanic island in the Gulf of Guinea, and its climate in May is not what you would choose. Eddington's equipment was largely borrowed, because Cambridge Observatory wasn't set up for eclipse work. On the morning of the eclipse, it rained on Príncipe. The cloud thinned as totality approached, but never fully cleared. Eddington and Cottingham worked through it, changing plates on a fixed schedule, exposing into cloud because there was no way to know from moment to moment what was getting through. Eddington later said that of the 16 plates he exposed, he could see stars on very few of them. 2 were ultimately usable. 2 plates, from an expedition that took months and crossed an ocean. At Sobral, the sky was clear. The 4-inch performed beautifully. The astrographic, the instrument they'd expected to carry the result, did not. Its star images came out distorted and out of focus, blurred smudges rather than clean points. The most likely culprit was the coelostat mirror heating and deforming in the sun during totality. Nighttime comparison plates taken with the same instrument were sharp. Only the eclipse plates were bad. Then everything went into crates and waited for a ship. There was no other way to move it. The Sobral plates traveled back to England by sea, and the measuring, the micrometer work, the reductions, the arithmetic, occupied the summer and autumn. For months, nobody knew the answer. By autumn, 3 numbers existed. They did not agree. The Sobral 4-inch, the backup lens, gave the cleanest data of the entire enterprise. Its result, corrected to the solar limb, was 1.98 arcseconds, with a probable error of 0.12. Converting to the standard deviation used today, that's about 1.98 plus or minus 0.18. Above Einstein's 1.75, but comfortably in its neighborhood, and nowhere near the Newtonian 0.875. Eddington's Príncipe plates, those 2 survivors, gave 1.61 arcseconds, with a probable error of 0.30. On the modern convention, 1.61 plus or minus 0.45. Below Einstein's value, but again, far from the half deflection. The eclipse report was explicit that a large part of that uncertainty came from possible systematic errors, not just statistical scatter. And the Sobral astrographic, the blurred one, gave something else entirely. Depending on the assumptions made in reducing it, it came out at roughly 0.93 arcseconds, or on one treatment about 0.90, or on another as high as 1.56. The report characterized it as discordant by an amount far beyond the limits of its accidental error, and described one of those solutions as a result of little weight. So one instrument gave a number slightly above Einstein, one gave a number slightly below Einstein, and one gave a mess that, on the most straightforward reading of it, pointed at Newton. The astrographic result was set aside. And that decision is the single most contested thing in this entire story, so let's be precise about it. The standard accusation, which entered wide circulation through a 1980 critique by philosophers John Earman and Clark Glymore, was that Eddington threw out the data that disagreed with him. In that telling, Eddington was a committed relativist who wanted Einstein to win, and he suppressed the negative Sobral result and leaned on his own weaker Príncipe plates to get the answer he'd already decided on. It's a compelling story. It's also, on the historical evidence, wrong in its central claim. Detailed work by Daniel Kennefic has established that the two expeditions' plates were reduced and analyzed separately. The Sobral plates, including the astrographic, including the decision to exclude it, were handled by the Royal Greenwich Observatory team under Dyson. Eddington worked independently on the Príncipe data. Attributing the Sobral data selection to Eddington is not historically accurate. Dyson led that call, and Dyson was not a partisan for Einstein. There's more. In 1979, 60 years on, the Royal Greenwich Observatory remeasured the surviving original plates using modern equipment and modern reduction methods. The reanalysis supports Dyson's decision. The astrographic data really was compromised. The distortion really was an instrumental artifact, and excluding it was defensible on grounds that have nothing to do with what answer anyone wanted. Which does not mean the 1919 team was faultless. They made judgment calls under pressure with limited data, and they presented their result with a confidence that the error bars didn't fully earn. But they cooked the books is a claim that modern scholarship has taken apart fairly thoroughly, and it's worth knowing that the version circulating on the internet is the version that was refuted. On 6 November 1919, the results were presented at a joint meeting of the Royal Society and the Royal Astronomical Society in London. Dyson presented the Sobral results. Eddington presented Príncipe. The conclusion offered to the room was that the expeditions left little doubt that light is deflected in the vicinity of the Sun by an amount consistent with Einstein's theory. They also said, in the same breath, that more data was needed and that the observation should be repeated at future eclipses. That second part didn't make the newspapers. What made the newspapers was the collapse of Newton. The press coverage in the days that followed was extraordinary. Headlines about a revolution in science, a new theory of the universe, Newtonian ideas overthrown. And this landed 1 year after the armistice, in a Britain exhausted by war, and the story it offered was irresistible. British astronomers had sailed out to test the theory of a German physicist and had honestly confirmed him. Einstein, who had been essentially unknown outside professional physics, became within weeks the most famous scientist alive. He remains, more than a century later, the public's default image of what a genius looks like. That fame dates precisely to this week. But look carefully at what had actually been established. 3 plates worth of data, 2 usable images from one site, 1 backup instrument carrying the weight at the other, error bars of 10 to 30%, a third instrument discarded, and a result that, taken at face value, ranged from 1.61 to 1.98 against a prediction of 1.75. That is enough to rule out zero deflection. It is enough to rule out the half deflection. It is not enough to confirm general relativity, and the astronomers who did it said so in the room. What 1919 accomplished was narrower and, honestly, more interesting than the headline. It eliminated 2 of 3 candidate answers and established that the remaining one was in the right range. It converted general relativity from a mathematical proposal into a theory with observational support that had to be taken seriously. The confirmation came later, piece by piece, over decades. The next major eclipse attempt came in 1922, observed from Australia, at a sheep station in the outback. More expeditions followed through the 1920s and 1930s and beyond. Eclipse measurements of light deflection continued for most of the 20th century, and they had a persistent problem. They never got dramatically better than 1919. The systematic errors, the heat, the mirrors, the plate scale, the few minutes of totality, put a floor under the accuracy that no amount of care could break through. The breakthrough came from changing what you observe with. Radio astronomy transformed the problem. Radio waves from distant quasars are deflected by the sun exactly as visible starlight is, but radio telescopes don't care about daylight. There's no need for an eclipse at all. You can watch a quasar pass near the sun anytime it happens, and repeat it as often as you like. Very long baseline interferometry took it further, linking radio telescopes across continents into a single instrument with an effective aperture the size of the Earth, delivering positional accuracy measured in micro-arcseconds, millionths of an arcsecond. The results are usually quoted in terms of a parameter called gamma, which measures how much space curvature a given mass produces. General relativity says gamma equals exactly 1. The Newtonian half deflection corresponds to gamma equal to 0. Global VLBI datasets have pinned gamma to 1 within roughly 0.02%. Then came Cassini. On its way to Saturn, the spacecraft's radio signals passed close to the Sun, and the delay and deflection of those signals were tracked with a sophisticated multi-band radio link designed to subtract out the interference from the solar corona. That experiment, published in 2003, constrained gamma to about 2 parts in 100,000. Put those on the same scale. In 1919, they measured this effect to something like 30%. Cassini measured it to about 0.002%. That's an improvement of roughly 4 orders of magnitude, and it's the reason we can say general relativity has been confirmed, in a way that 1919 alone never could. There's a lovely footnote to all this. In 2017, during the North American total eclipse, a retired optical physicist named Donald Bruns repeated the 1919 experiment as an amateur, with modern commercial equipment and a digital sensor. He measured the deflection at 1.7512 arcseconds, with an uncertainty of about 3%, limited mainly by atmospheric turbulence. One person, consumer-grade gear, a result 10 times more precise than 2 funded expeditions achieved in 1919, and sitting almost exactly on Einstein's predicted value. That comparison isn't a criticism of Eddington and Dyson and Crommelin and Davidson. It's the opposite. It shows exactly how difficult the thing they attempted was, and how much of what they were fighting was simply the technology of their moment. So what did the 1919 eclipse actually change? Not the truth of general relativity. That was settled by the accumulated weight of a century of increasingly precise measurement, and the eclipse is the first and crudest data point in that series. What it changed was which theory physics took seriously enough to keep testing. Before November 1919, general relativity was an elegant mathematical structure with one modest observational success to its name. After November 1919, it was the framework you had to work within, and every subsequent test was an attempt to break something that had already earned the benefit of the doubt. And the practical consequences of that framework are now sitting in your pocket. Satellite navigation depends on clocks in orbit staying synchronized with clocks on the ground, and those clocks run at measurably different rates because of exactly the effects general relativity describes. The corrections are built into the system. Without the physics that the 1919 eclipse first pointed at, the navigation on your phone doesn't work. Gravitational lensing, the same light-bending effect, produced by entire galaxies instead of one star, is now a standard tool of astronomy. We use it to weigh dark matter and to see objects too distant to observe any other way. The distortion Eddington was straining to detect at 2 arcseconds is now something astronomers use routinely as an instrument. But the part of this story that I keep coming back to isn't the physics. It's the honesty problem. 3 instruments went out. 1 produced excellent data, 1 produced marginal data, and 1 produced data that had to be thrown away. The team announced a result that was consistent with Einstein but not tight enough to nail him down, and they said so, and the world heard something more certain than what they'd said. A century of argument followed about whether the discarded plates were discarded honestly, and the answer, on the evidence, appears to be yes, though it took decades of historical work to establish that. The eclipse of 1919 wasn't a moment of proof. It was the moment a question stopped being philosophical and started being a measurement, one that got made again and again and again, each time a little more precisely, until the answer was no longer in doubt. That's slower than the headline version. It's also how it actually works.